separating the source from the sink has capacity less than n-half. So we let the number of edges in the cut incident to the source be n plus and incident to the target n minus. And so this is the overall number of edges. And moreover, we can say that the cut consists of the edges in the graph separating at least n over 2 minus n plus vertices in BT, this is BT, from n2 minus n minus vertices in BT bar. The expansion is, I can say the expansion is less than 2 over C times n2 minus n plus minus n minus divided by mean of n2 minus n plus and n2 minus n minus. This is the definition of expansion. You know, expansion is number of edges going from S to S bar, minimum of cardinality of S and S bar. You remember this? This is exactly this. This one is minimum of this, but here we miss some n plus points. And we miss some n minus point from the target, and we miss some n plus point from the source. So this is all of the crossings. So this is the S, this is the cardinality of S, this is the cardinality of S bar. And in the denominator, I showed you that the number of edges going from S to S bar is this. So it is reduced by this C. And so it is almost complete. The proof is complete. Note that if the max flow has value n over 2 minus v, then n plus and n minus is greater than that v that we reduced. So you can see the paper is very easy to understand. And the final proof, the theorem 2.1 is the heart of this article. And in order to prove it, we used lemma 3.7 that the sparsest of cut computed by max flow has expansion at most 2 over C max because the expansion is bounded by this. And of course, by another lemma, I showed you that psi of t is less than 4n2. This says that expansion of h of t, expansion, is greater than 1 over 2. So the union of the matchings has expansion at least half with high probability. So we run the algorithm for order of log 2n rounds, as I said. And since each matching was embedded, so this is G, this is H. After some matchings, you get some graph here. And so each matching was embedded with congestion at most C max, which is maximum of all of these capacities in round L, for example, over all rounds. So their union is embedded in G with congestion order of C max log 2n. And this establishes that G has expansion 1 over C max log 2n. And the approximation factor for expansion is log 2n. And then it remains to show that we can bound the running time log 2n. And for that, flow match, you use for flow match, after flow match, we use the binary search, as I said, binary search. Remember, I said the flow C is fixed. The flow is fixed, is n over 2, and we find C. What C should I give in order to get n half? So it's a binary search. And so the binary search for a capacity C that the flow problem yields a flow of capacity n over 2, but capacity n over 2 is infeasible. So you have the highest quality if all of them goes to the other side. So 1, 1, 1, 1, 1, 1, 1, 1, and C, 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 C. So this is the perfect. So for all of them, the flow is 5, but the capacity is different, because in each cut you see different size of this complex G. For example, sometimes this is your cut, so you see some edges like this. Sometimes you have this cut, so you only see these vertices. Sometimes this cut. So we have different combinations of cuts, and that's why your C is different in each round. And so we have a cut quality sequence. For example, sometimes like this, the cut quality is 100%. Sometimes you have 95%, 10%. This is the sparsest cut. And sometimes 70%. So it's a sequence, like a Turing machine. So it's a sequence, and the capacity at each round is different. So capacity is also a sequence. C over 2, sometimes C over 3, sometimes 2, 3 over 3. So it's a sequence as well. So a bad scenario could be some edges are wasted, like people in third world countries. And some edges, the bad scenario, for example, could be the source is going to all of them, but this one is incident. As I said, this edge is incident. And so we lose the opportunity and potential for some people in third world countries like this. And you go to target, T. So we have a cut here, B and B bar. And so as I said, this could be possible. This could be incident as well. So here, because of this edge, n minus 1 is 1. Because of this edge, n plus is 1. And we can say that so this is an example that you can imagine when you want to see what we are doing. But the next paper I want to show you is the paper of expander flows, geometric embedding, and graph partitioning. It's 2004, and it's 2009. It is accepted in ACM. It is written by people like Sanjeev Arora, my favorite, Satish Rao, the guy who also is active on metric embedding, Umesh Vazirani, There is another Vazirani who is also genius like him. It's Vijay Vazirani, the author of Approximation Algorithm. So these three guys they wrote a paper about finding optimal separators. And they approximate that order of log n approximation for sparsest cut using semi-definite principle, as you could imagine. And the integrality gap of this is order of log n. So it's quite an improvement. And because, there is a guy, Lighton in MIT, and Satish Rao, in 1999, it's an old article, O log n, they achieved O log n using linear programming. But this time they're using semi-definite programming. For linear programming, they couldn't go up to integrality gap of log n. And so here they used multi-commodity max-flow cut theorem. They wrote an article called Multi-Commodity Max-Flow Cut Theorems and Their Use in Designing Approximation Algorithm. It's 46 pages, but it is very important. Each sentence of that article is important. And they introduced geometric embedding. Geometric embedding is just minimize over all f, the distance between f of u and f of v, omega of u and v, and f assigns to hv some points in Rd. And so the dual of this is important. The dual of the K commodity flow is finding distance d of E, such that for any edge, d of source and sink greater than 1, so that C of E, d of E is minimized. And to understand many things, you need to learn this article that O log n approximation to sparsest cut in O tilde n2 time, again by Sanjeev Arora, but this time with Guy Elad Hazan and Satyen Kale. Sanjeev Arora, my favorite. And so let's talk about some definitions that we need for the results. Some definitions. For example, you need to know what is a uniform sparsest cut. I've defined this several times. This is the minimum of number of edges between S and S bar over cardinality of S and S bar. And the cardinality of S should be less than cardinality of S complement. And since V over 2 is less than S bar, less than V up to factor 2, computing the sparsest cut is the same as computing the edge expansion. And what is edge expansion? Alpha of G is minimum of edge of S and S bar over S. And the conductance also is interesting. The definition of conductance, phi of G, all of them are almost equal. They're very similar. So this is the number of edges from S to S bar over number of edges of S. And what we are going to do is very interesting. We are assigning some vectors to any vertex. So what is L22 representation? So by definition, it's an assignment of a vector to each node. So we assign vector vi to node I. But it should satisfy the triangle inequality, which is vi minus vj squared plus vj minus vk squared is greater than vi minus vk squared. And an L2 representation is called a unit L2 representation if all points lie on the unit sphere, or equivalently, all vectors have unit length. And finally, you need to know what is alpha C of G. This is the minimum edge expansion among all C balanced cuts. And what is C balanced cut? It's the same cut, but now the cardinality of S should be at least C times the cardinality of V, and same for the complement of that. And every cut S and S bar gives rise to a natural unit L22 representation. And this is interesting. So now I want to show you the following STP. This STP is a relaxation of alpha C of G. This is a relaxation of that, and is scaled by Cn. So we want to minimize Vi minus Vj squared. Remember, in MaxCut, we wanted to maximize this, but now we want to minimize this. So for any I, we know that it should be length 1, and it should satisfy the triangle inequality, as I said. This is the triangle inequality. And also something interesting. Also, it should satisfy this. Vi minus Vj squared for C, 1 minus Cn squared. What the hell is that? But it's very interesting. So this might be new for you, but if you prove that, you will see why this plays an important role. So this is the condition 7 in the original paper. So this is the STP. That is a relaxation for the alpha C of G. And also you can formulate another STP. And L2 representation is C spread if that constraint that I showed you is satisfied. And this one is a relaxation for sparsest cut, which is the minimization of Vi minus Vj. Again, you have triangle inequality, but here Vi minus Vj squared is 1. This is the sparsest cut problem. And I can say that STP covers two popular methods. Eigenvalue approach, which is Laplacian approach, L is D minus W. This is diagonal, this is adjacency. And also STP can cover Lighton-Rao. Why? Because they used linear programming. SDP is a generalization of linear programming. So optimum value of sparsest cut